I get this question all the time. People come up to me and they say, Mr. Feynman, we went to the moon, right? We built rockets. We sent men up there. They walked around. They came back. So why can't we just, do the same thing but go further? Why can't we go to the stars? And I look at them and I smile because it's such a beautiful question. It's the kind of question that shows human optimism, human ambition. But it's also the kind of question that shows we don't really understand the numbers. And in physics, my friends, the numbers are everything. They don't lie. They don't care about your dreams or your science fiction movies. They just sit there, cold and honest, waiting for you to do the arithmetic. So today, I want to explain to you why going to the moon and going to the stars are not just different in degree. They're different in kind. They're different beasts entirely. Now, let me start by saying something important. The moon landing was absolutely magnificent. It was one of the greatest achievements in human history. We took a bunch of metal. We filled it with explosive fuel. We put 3 brave men on top of it, and we shot them 250,000 miles into space. Then we landed them on another world, and we brought them back home safely. That's extraordinary. That required incredible engineering, incredible courage, and incredible precision. But here's what people don't realize. The moon is our neighbor. It's right next door. It's like living in New York and taking a trip to Philadelphia. Sure, you need a car, you need some planning, but it's doable. The stars? The stars are like trying to walk to China, except China is 1,000,000 times further away, and there's no ground to walk on, and you can't breathe. And if you make one tiny mistake, you die in the most absolute, permanent way imaginable. Let me show you what I mean by doing something physicists love to do. Let's calculate. Let's look at the actual numbers and see what nature is trying to tell us. First, let's talk about distance. The moon is about 240,000 miles away from Earth. That's 384,000 kilometers for those of you who prefer sensible units. The Apollo astronauts got there in about 3 days. 3 days. That's a long weekend. You could leave on Friday and be back by Monday morning if you skipped the moonwalk. Now, what about the nearest star? The nearest star to us, besides our sun, is Proxima Centauri. It's part of the Alpha Centauri system, and it's about 4.24 light years away. Do you know what a light year is? A light year is the distance light travels in 1 year, and light is fast. Light is the fastest thing in the universe. It goes 186,000 miles every single second. Every second. In the time it takes you to say 1 Mississippi, light has traveled far enough to circle the Earth 7.5 times. So when we say Proxima Centauri is 4.24 light years away, we mean that if you could somehow travel at the speed of light, which you can't, by the way, but if you could, it would still take you 4.25 years to get there. But we can't travel at the speed of light. The Apollo spacecraft traveled at about 25,000 miles per hour at its fastest. That sounds impressive, doesn't it? But let's do the arithmetic. At that speed, how long would it take to reach Proxima Centauri? The answer is about 100 to 15,000 years. 115,000 years. That's longer than recorded human history. That's longer than modern humans have existed as a species. You would launch the mission, and by the time it arrived, your civilization would have risen and fallen dozens of times over. Do you see what I'm getting at? The moon is 240,000 miles away. Proxima Centauri is 25 trillion miles away. That's not just bigger. That's 100 million times further. 100 million. If going to the moon is taking 1 step, Going to the nearest star is taking 100 million steps, and you have to take them all in space, with no air, no food growing anywhere, no place to stop and rest. But distance is just the beginning of our problems. Let's talk about energy, because energy is really where things get impossible with our current technology. When you want to go somewhere in space, you need to accelerate. You need to push yourself up to speed. And the faster you want to go, the more energy you need. This isn't negotiable. This is just physics. The rocket equation, which was worked out by a Russian fellow named Tsiolkovsky, tells us something very depressing. It tells us that the amount of fuel you need grows exponentially with the speed you want to achieve. Not linearly. Exponentially. That means if you want to go twice as fast, you don't need twice as much fuel. You need 4 times as much. Or 8 times. Or more, depending on your rocket design. Let me give you a concrete example. The Saturn V rocket, which took us to the moon, was enormous. It weighed 6.5 million pounds when it was fully fueled. Do you know how much of that was the actual spacecraft that went to the moon? About 100,000 pounds. Everything else, all those millions of pounds, was fuel and rocket stages that were thrown away. So we used 6.5 million pounds of rocket to send 100,000 pounds to the moon. That's a ratio of 65 to 1. And the moon is right next door. Now, what if we want to go to Proxima Centauri? What if we want to go even a tiny fraction of the speed of light, say 10%? That's still 186,000 miles per second divided by 10, so 18,600 miles per second. At that speed, the trip would take 42 years. 1 human lifetime. That seems doable, right? Wrong. To accelerate even a small spacecraft to 10% the speed of light using conventional rockets would require more fuel than exists in the entire solar system. I'm not exaggerating. You could mine every planet, every moon, every asteroid, turn it all into rocket fuel, and you still wouldn't have enough. Why? Because of the tyranny of the rocket equation. You need fuel to accelerate your fuel, and you need fuel to accelerate the fuel that accelerates your fuel. It spirals out of control very quickly. And remember, we haven't even talked about slowing down when you get there. If you accelerate to 10% the speed of light, you're going to zip right past Proxima Centauri unless you can brake. And braking requires just as much energy as accelerating. So now you need twice as much fuel. And if you want to come back, forget about it. Now you need 4 times as much fuel. The numbers just don't work. Not even close. Let's say we somehow solve the energy problem. Maybe we invent some incredible new propulsion system. Fusion rockets, antimatter drives, solar sails pushed by giant lasers, whatever. Let's say we can actually get up to a decent fraction of the speed of light. We still have the time problem. Even at 10% light speed, the nearest star is 42 years away. That's a human lifetime. You would leave Earth as a young person, and you would arrive, if everything went perfectly, as an old person. Your children, if you had them on the ship, would be middle-aged. Your grandchildren would be the ones who actually got to explore the new world. And that's the nearest star. There might not be anything interesting there. No habitable planets, no resources worth the trip. If you want to go somewhere more promising, you're talking about hundreds of years. Thousands of years, potentially. This creates enormous problems. How do you keep humans alive for that long in a tin can flying through space? How do you grow food? How do you recycle air and water with perfect efficiency for centuries? One small mistake, one system failure, and everyone dies. And then there's the social problem. How do you maintain a civilization on a spaceship for generations? How do you keep people motivated to continue a mission they didn't start and won't finish? How do you prevent conflicts, maintain technology, preserve knowledge? We went to the moon and came back in 8 days. If something went wrong, if there was an emergency, we could abort and come home. With interstellar travel, there is no abort. There is no coming home. You are committed absolutely. You either make it or you die trying, and you won't even know which for decades or centuries. And speaking of dying, let's talk about all the ways space tries to kill you. On the moon mission, the astronauts were exposed to cosmic radiation, but only for a few days. Not ideal, but manageable. On an interstellar voyage, you're exposed for decades, centuries maybe. Cosmic rays are high-energy particles that zip through space at nearly the speed of light. They come from supernovas, from black holes, from all sorts of violent cosmic events. When they hit your body, they tear through your cells, damaging DNA, causing cancer, degrading your tissues. On Earth, we're protected by our atmosphere and our magnetic field. On a spaceship, you're naked to the cosmos. You could try to shield yourself with thick walls, but thick walls are heavy. And remember, every pound of shielding is a pound you have to accelerate and decelerate, which requires more fuel, which makes the energy problem even worse. And it's not just radiation. There's micrometeoroids, tiny specks of dust and rock traveling at incredible speeds. At 10%, the speed of light, even a grain of sand hitting your spacecraft releases as much energy as a stick of dynamite. Your ship would need to be armored like a battleship, which again makes it heavier, which makes the energy problem worse. Then there's the psychological effects, the isolation, the boredom, the knowledge that you can never go back home, that everyone you knew on Earth is dead or will be dead long before you arrive anywhere. That's not a technical problem, but it's a real problem. So why did the moon work? Why were we able to do that? Because the moon is close. Because the trip was short. Because we could use chemical rockets, which are relatively simple and well understood. Because if something went wrong, there was at least a chance of rescue or abort. Because the astronauts only had to survive for days, not years. The moon landing worked because it was just barely at the edge of what's possible with mid-20th century technology and a lot of money and determination. We pushed ourselves to our absolute limit, and we made it work. It was glorious. But interstellar travel isn't at the edge of what's possible. It's not even close. It's so far beyond our current capabilities that it might as well be magic. The gap between going to the moon and going to the stars is not like the gap between building a bicycle and building a car. It's like the gap between building a bicycle and building a device that violates the laws of thermodynamics. Now, does that mean interstellar travel is impossible? No. I never say anything is impossible. Nature doesn't care what we think is possible. Nature just has rules, and if you can work within those rules, you can do anything that the rules allow. But it means we need fundamentally new approaches. We can't just build bigger rockets. That doesn't work. The numbers don't allow it. We might need generation ships, where multiple generations of humans live and die on the voyage. We might need to freeze people, put them in some kind of suspended animation, though we don't know how to do that yet. We might need to send robots instead of humans, tiny probes that can accelerate to high speeds with less energy. There's an idea called Project Starshot, where you build a tiny spacecraft, just a chip really, with a big light sail attached to it. Then you point an incredibly powerful laser at it from Earth, and you push it up to 20%, the speed of light. At that speed, it could reach Proxima Centauri in about 20 years. But it couldn't slow down. It would just zip past, taking pictures, sending data back to Earth, which would take another 4 years to arrive. That might work, but it's not humans going to the stars. It's sending a postcard to the stars. If we want humans to go, we need breakthrough technologies. Fusion propulsion. antimatter engines, maybe even things we haven't thought of yet. We need ways to generate enormous amounts of energy with very little mass. We need perfect recycling systems. We need to solve biological problems we barely understand. It's not impossible, but it's hard. Really, really hard. So when someone asks me, we went to the moon, why can't we go to the stars? I tell them this. The moon was an incredible achievement. It showed what humans can do when we work together, when we apply our intelligence and our resources to a difficult problem. But going to the stars is a different beast entirely. It's not just harder than going to the moon. It's harder in a way that requires completely new physics, new engineering, new biology. It requires us to become a different kind of civilization. And maybe we will. Maybe in 100 years or 1,000 years, humans will figure it out. Maybe they'll look back at us and laugh at how primitive our rockets were, the same way we look back at sailing ships and think how quaint they are. But right now, today, with what we know and what we can build, interstellar travel is not like going to the moon. It's not just a matter of building a bigger rocket or having more courage. It's a matter of the numbers, and the numbers are brutally, honestly, magnificently clear. They tell us that the universe is big, unimaginably big, and we are small. And the gap between those two things is not easy to bridge. But you know what? That's okay. That's part of what makes it interesting. If it were easy, it wouldn't be worth doing. The fact that it's hard, the fact that it requires us to push the absolute boundaries of what's possible, that's what makes it beautiful. So yes, we went to the moon, and that was magnificent. But the stars? The stars are waiting. They're waiting for us to get smarter, to get more creative, to really understand the deep laws of nature and figure out how to work with them. And when we do, when we finally make that journey, it'll be even more magnificent than the moon landing. It'll be the next great chapter in the human story. But we're not there yet. Not even close. And that's the honest truth. Thank you.